to summarize this fault detection, so we can this table actually summarizes the different faults that are detected, like MATS ++ detects Takat fault and address decoder faults, and this is the corresponding March sequence. March X determines these faults, March Y determines. So, these are some of the well known March sequences that have been reported in the literature, and they are there. So, apart from these also there are many other March sequences that you can find in the literature, and accordingly different authors, they have claimed different types of faults getting detected by them. So, this is another comparison. So, you see that this March C minus, so this covers most of the faults excepting this Tuck open fault, whereas say then March Y, March X. So, these are the different faults, there are different algorithms, they could cover some of these algorithms, some of those faults. Another way of looking into memory testing is the word oriented memory. So far whatever we were looking into, so we are assuming that we can access individual cells of the memory separately, and then we can modify, we can do a read write operation on the individual cells. Some of the memories are word oriented, where the access is for the entire word. So, if there actually we can also use this March based testing, March testing mechanisms for doing the memory testing. So, word oriented memory, it has read write operations that access the memory cell array by a word instead of a bit. So, they can be tested by applying a bit oriented test algorithm repetitively with a set of different data backgrounds. So, this way, so we can say we can just do it for every bit of the word. So, we can repeat the process. So, that is one possibility. So, naturally, since we are repeating for every bit, so the testing time will be more. So, another way of doing it is to we can do it in a word oriented fashion. So, background bit, instead of talking about the background bit, we talk about background word. For example, this MATS ++ algorithm, so we can talk about write A, where A is a word pattern. So, if your word is 8 bit, then A may be all zeros, or A may be also alternate 0 1s. So, it is a 8 bit pattern. Similarly, so read A and write B. So, since we have written a value A, pattern A, so we are expecting to read a pattern A, then we are writing another pattern B, then we are expecting to read the particular pattern B here, then write a read A. So, this is the MATS ++ in a word oriented memory. So, if I have got m bit words, then we can have different backgrounds, like log m +1 different backgrounds are used. So, this is a standard, so these are called standard backgrounds. So, basically these are the backgrounds, like if m equal to 8, so it means that there are 4 standard backgrounds, and these are the standard backgrounds. So, all zeros, then alternate 0 1s, then 2 0 2 1. So, runs of zeros, basically here it is a runs of 8 zeros. So, it is a run of 1 0, there is a run of 2 zeros, it is a run of 4 zeros. So, that way we can have or you can read this one as run of 4 zeros, run of 8 zeros. So, 1 0 2 0 4 0 8 0. So, you can read it like that. So, these are called standard backgrounds. So, for each of these background, so we will be applying the test algorithm. So, since it is 4, the complexity will become 4 into 6n by 8, because there are 6 elements in this sequence, 6 operations. So, 6 into n. So, and that divided by 8, because I am doing it every word at a time. So, n by 8 is the number of words in the memory. Memory has got n bits. So, n by 8 is the number of words. So, total number of operations is 3n. Okay. So, B has to be complement of A. So, otherwise you will not be able to detect that stuck at 0 or stuck at 1 type of situation. So, this B has to be complement of A. So, there is a cocktail march class of algorithms known as cocktail march algorithms. So, it says that repeat the same algorithm for all log m +1 backgrounds is redundant, because there may be intra-word coupling faults when we are considering only intra-word coupling faults. So, this is redundant. So, intra-word coupling fault means within the same word 2 bits are coupled to each other. Okay. So, we can have some different algorithms, we can target different faults. So, what it says? It says that use multiple backgrounds in a single algorithm run. So, in the same run, so we use different different backgrounds, merge and forge different algorithms into and backgrounds into a single algorithm. So, this is what is looking for. So, the for word oriented memory it will be good. So, this is basically the thing that we are talking about. So, say march CW, march CW, it says that march C minus is using the solid background 0 0 0 0, then a 5n march of each of the other standard backgrounds. So, 0 0 0 0 1 0 1 and 0 0 1 1. So, this will be done like this. So, write A, write B, read B, write A, read A. So, you see there are two backgrounds A and B. So, they are being used, and so that way we can do it. So, the complexity is given by this expression 10 plus 5 log m into n, and the test time is reduced by 39%. So, this as your memory size increases or the word size increases, your improvement will also increase, percentage improvement will also increase. Another type of memory that is common is known as multi-port memory. So, multi-port memory means you can there are say more than one read write port available. So, you can do more than one read write operation to the memory simultaneously. So, this is particularly useful if we have got a multi-processor system. So, different processors, so they will ask for content from memory or different memory location content. So, if the problem with single port memory is that even if I have got multiple processors, so they will have to wait for memory access which is sequential in nature. So, if I have got multi-port memory, then they can be accessed parallelly. So, the problems that can occur in multi-port memory, so they apart from this cell faults which is traditional, so we can have port faults. So, port fault is a stack open fault, then this address decoder fault and multi-port fault. So, these are known as port faults. So, multi-port fault means across ports, so there is a problem. So, apart from that we have got the standard cell faults like stacked fault, transition fault, read destruction fault. So, like that. So, we have got those faults, but apart from that we have got port faults. So, this is a 2-port RAM topology. So, you see that there are, as I have said, that there are 2 ports. So, one port is port A, another is port B. So, for port A we have got bit line A and bit line A bar. So, they are bit line A and bit line A. So, these are the first line. So, they are corresponding to bit line A, and then the second line. So, they are corresponding to bit line B. Similarly, while going like this, so these are the word lines. So, we have got word lines for port A and word lines for port B. Now, if there is a inter-port word line short, so if these two lines are shorted, so that is WLB is getting shorted with WLA, and similarly another possibility is inter-port bit line short. So, this bit line A is getting shorted with bit line A of bit line B is getting shorted with bit line A. Okay. So, that way there can be this type of faults, they are known as multi-port fault or inter-port fault. Now, what is the situation? So, in a if there is a word line short, then in a fault free access, port A if put address 1, so it will be accessing cell 1, port B you put address 2, so it will be accessing cell 2. In a faulty situation, address 1 accesses cell 1. So, so if it is a case of word line short, so we are talking about so this particular short. So, word line A it accesses a particular cell. So, word line A is so this one. So, it is accessing cell 1 as we see here. So, word line A, the address 1 is accessing cell 1, but word line B, so this is actually shorted. So, word line B, so word line B is shorted here. As a result, it will access for address 2 it will be accessing cell 2 and cell 3. For address 3 it is accessing cell 3, but for while it is putting address 2, okay, so it will be accessing cell 2 and cell 3. So, this word line B, so this is shorted with word line 2. So, when it is trying to access this cell 2, so it is also accessing cell 3. So, that way the complexity will become of course, this big O n cube. So, their complexity is high, but this may be the situation. Similarly, this bit line sort. So, here also fault free situation, this address alpha will access cell alpha, address beta will access cell beta, but in a faulty situation. So, address alpha will access in port A cell alpha and cell beta, and this address beta in case of faulty situation. So, it will access cell alpha and cell beta on port B. So, that way we can have multiple locations access. So, this address decoder part, so they become faulty because of this word line and bit line shorts. Okay. So, these are about multi-port. So, there are some test pattern generation techniques for testing this multi-port faults. Now, this another type of this memory for test algorithm generation is via simulation. So, what we do is that we generate some test algorithm and do a simulation to see whether it can detect a number of faults or not. So, this so many times this memory fault simulation is done. So, why is it so important? So, it has to be done efficiently when the number of fault models is large. So, fault coverage evaluation will be done efficiently. So, if the number of fault models are large, then if you want to simulate if you want to check whether the faults are getting covered or not, then for each of the fault models, so you have to simulate the memory once. So, if we are doing like this, then it will take huge amount of time. So, an efficient evaluation means I will be simulating the memory for multiple fault models simultaneously. So, as a result, the fault coverage evaluation will be faster. So, again this bit oriented and word oriented memories can also be simulated, and test algorithm design and optimization can be done in a much easier way. So, why? Because test algorithm design is nothing but proposing some new march elements or march sequences. So, since I have got a simulator, so I can immediately check whether which faults are getting covered by the new pattern that we have, new test element that we have introduced into the test. So, that way if the fault simulation is strong, then we can do it fast. So, detection of a test algorithm on unexpected faults can be discovered. So, for some unexpected faults means some faults that we did not model previously also. So, that can be that can get detected by a test pattern or test algorithm. So, that will also happen due to this fast fault or efficient fault simulation. And faults dictionary can be constructed for diagnosis. Okay. So, I can identify which locations have failed, and accordingly we can identify like which cells are faulty and try to do a replace and all that. So, this is a typical example. Say we are doing a sequential memory fault simulation. So, complexity is n cube for 2 cell coupling fault. Why? Because if we have to check a 2 cell coupling fault, then if there are n number of cells, then there are n square type of coupling. So, we can choose 2 cells. So, n choose 2. So, it is n square number of coupling faults that can occur. Now, for each of these faults, so I need to inject the fault, and for each of the test element, okay, so we have to apply the test element and report the error output. So, this has to be done for march test, at least n operations are to be done. Okay. So, we have to apply. So, it is say at least some constant multiplied by n. For march algorithms we have seen it is 4n, 6n like that. So, it is again some sort of n. So, this n into n square. So, this is the overall complexity becomes n cube, and n being large, this n cube is going to be prohibitively high. So, if we are doing a sequential memory fault simulation, so we do not get the correct answer, because we have to correct answer in the sense that with the amount of time that is needed to do the simulation, so that we may not be able to afford that time. So, what is done is the parallel fault simulation. So, this is one technique Ramsey's that has been reported in 2002, where each fault model has a fault descriptor. So, what it says is that, so it's the first fault that we are considering is stuck at 1. So, it has got a descriptor. How? So, it has got a aggressor. The AGR is the aggressor. So, So, aggressor pattern. So, that is which will create the detection of that particular fault. So, this is basically if I do a write operation. So, this is the aggressor write 0. So, I want to excite this stuck at 1 fault. So, naturally I have to write a 0. Then this is the suspect. So, whom are you suspecting? You are suspecting the same cell. So, it is at the rate means same cell we are suspecting. Then what is the victim marking? Victim marking I can do by doing R0. So, if I read now, read and expect a value 0, and the how to recover from this? So, we have modified the cell content to 0 by the aggressor. So, you have to write a 1 to go back to the to recover from the fault, because this is stuck at 1. So, if it is written 1, that means the fault will go from the cell. So, this is actually a pattern. So, this tells that if you find that a particular algorithm, particular test algorithm, it is first writing a 0, then it is doing a read 0, and then it is doing a write 1. In a march element it is doing that. That means that particular march element can detect stuck at fault at that particular cell. Similarly, we can determine this coupling fault. This is so it is 0, and then go from there it is going to stuck at 1. So, this way we can again identify the aggressor pattern. So, it is rising, it is V0, then this is the suspect are all other cells, then we are reading the content 0 as the victim, and for recovery we have to write a 1 here. So, this way we can, so this actual notations like V and W, so they are documented in this paper. So, I am not going into that, but essentially what it says is that in the template I should have this type of patterns, and from there we can identify that this particular test pattern is going to identify that fault. So, what it says is that for each test operation, so this is the Ramsey's algorithm. So, it says that for each test operation, if the operation that we are doing is an aggressor, then mark the victim cells. Like if we find that on a cell we are doing some aggressor operation, writing 0 at a cell or writing 1 at a cell. So, what are the victims? So, we can mark the corresponding victims. And then if the operation is recovery, then we release the victim cells. So, we have to write back the original values that should be there, the recovery, and if the operation is victim, then we report error. So, victim, you see that in this case victim is R0. So, if you find something else, so R1, if you get the value as 1, that means you can that is so the victim is detected. So, we can report an error. So, this way all the templates, all the templates that we have in a march in a test algorithm, so they can be tested parallelly and for all the types of faults that you are going to detect. So, what we have to do is that for all the fault models that you want to consider, so you have to write down the corresponding descriptors like this, and then for the test algorithm that you have specified in terms of march elements. So, you can do this for each test operation. You can figure out whether this aggressor part is matching, and if the aggressor part is matching, then which one is the victim and all that. So, that you can do. So, this is the Ramsey's algorithm. So, this is in detail it is telling. So, it is telling that for each operation set operation flags. So, if aggressor is a subset of operation flag, that is aggressor is there in the operation flag like W0. So, that is an aggressor. So, this aggressor is there in the operation flags. Then for each victim cell we say, so we set the victim flags and set aggressor address, which address has created this aggression. And on the other hand, if operation is recovery, then we have to clear the victim flag and clear aggressor entry. Otherwise, if operation is victim, then we say that it is detected. So, that way while doing the simulation, so if we find that this victim got detected because of the difference from the expected value, so this we say that the fault getting detected. So, it is irrespective of the fault model that we are considering. That is the beauty of this algorithm. So, it is not looking separately whether it is detecting a stuck at fault or coupling fault or transition fault like that. So, if it matches whichever template, whichever this whichever descriptor it matches, so that it has detected that particular fault. So that way it is irrespective of the fault model. So all fault models are being simulated parallelly in this mechanism. Okay. So these are the various sequence of various results, like this Takat fault. So this MATS plus plus is 100%. So all these also if all these faults. So if when we pass through this Ramsey's algorithm, so MATS plus plus, so it has found that all these faults, they can 100% can be detected. For coupling fault 75% can be detected. For coupling fault idempotent, so 37.5% can be detected. So these are the various measures that we can do. So if the Ramsey's algorithm was not there, then for each of these faults I have to do a separate simulation. So that will take a lot of time. Okay. So how can we do a test generation using this type of simulation? Okay. So given a set of target fault models, we want to generate a test set with 100% fault coverage. So that is what we are looking for, and other possibility is that given a set of target fault models and a test length constant, generate a test with the highest fault coverage. So one thing, first point tells that there is no restriction on the number of March elements we have. We can have any number of March elements until and unless we have got 100% fault coverage for the given fault model. So we go on adding elements to the March sequence. So that way we stop at 100% fault coverage, but naturally as we are adding more and more templates into that March sequence, so the complexity of the test algorithm is going up. So if there is a test length constant like say 7n or 10n or 15n like that, so how can we generate up a test set with the highest fault coverage? That is the other goal. So these are the two ways in which we can view the test generation algorithms. So either of these two. So we can have a priority setting for fault models. So we can say that okay, we will try to cover these fault models, and test length and test time can be reduced. So this is one possibility, and another possibility is that we can have a diagnostic test generation also. So we want to distinguish between the faults detected. So naturally for diagnostic test generation, so the test length will even be further longer. So this is the idea. So there is an approach known as test generation algorithm by simulation, or TAGS, TAGS. So what it does, first of all, this March templates that we have, they are abstracted. You see that in this particular sequence, so we can say that whether it is write 0 or read 0, it is not a big matter, but what matters is that it is a write operation and it is a read operation. So I can abstract it like this, as if this is a write operation, this is a read followed by write, this is read followed by write followed by read. So like that, and then we can also drop these arrows, up arrow and down arrows, and we can say okay, this is the template. Now you see that if we can generate this type of templates, so forget about the first two rows that we have here, we just concentrate on the last one. Suppose we can generate this type of templates which just does not have arrows, which does not have these 0 ones, then I can extend this to something like this. Okay, I can extend this by, so first it may be going up, it may be going down. So that way I can generate different types of sequences. Fine. So this may be up arrow, this may be down arrow, this may be again up arrow, or any of those variants. Similarly, this read and write operations, so this write may be a write 0 or it may be a write 1. Similarly, whatever be the write value here, this read value must be that one, and similarly whatever be the read value here, this write value should be complement of that. So that way I can generate some 0 1 combination. So if I started, so here this particular case it is starting with W0, I could have started with W1 also. So that way this particular abstracted template, so it can represent many of the actual March templates. So what these tags will do is that it will generate this type of templates and abstracted templates, and then it will populate those abstracted templates with those zeros, ones and up arrow, down arrows, and accordingly it will generate a sequence of a number of March element or March test sequences. And then I have got that Ramsey's algorithm by which you can evaluate the individual individual merge sequences, and we can take the best one from them. Okay. So, that is what is done. So, this is so we start with say a test length of 1 n. So, that is 1 n means it has to be a write operation, because I cannot start with a read operation. So, it has to be a write operation. So, start with a write operation, and then when I am trying to extend the length of this write. So, I can do it like this. I can put another write after this. Okay. So, I can add another element to this, which is a write, or I can in the same element I can put a read operation, or I can put a read as a separate merge element. So, these are the two different ways by which I can extend this element, this sequence having 1 n complexity to a sequence having 2 n complexity. Then from this again I can do extensions, and again I can get a number of such alternatives. Now, out of that you see this WW does not have any implication, because two successive writes. So, the last write will prevail. So, there is nothing to be detected. Similarly, this WW, so this also does not have much relevance, because they are all write operation, but this write followed by read. So, this is important, because we can write a value and then check the value of value that we have read, that we have written. And similarly, this WR, so this is also same thing. So, here actually for every cell I will do a write followed by read. Here we will do it for the entire memory, I will do the write, and then for the entire memory I will do the read operation in a sequence. So, this way we can have different types of templates. So, exhaustive generation complexity is very high, 6.7 million templates for n equal to 9. So, we have to use some sort of heuristics for restricting the number of ways in which we can generate the templates. So, this is the tags procedure. So, initialize with T1n equal to single W, and then increase the length by 1n, applying the generation options. Then we apply the filtering options to filter out the thing, then assign address order, okay, and data background. So, basically this address order up arrow, down arrow, and data background 0 and 1. Do a fault simulation using Ramsey's. So, ineffective tests will be dropped, and then we will some tests will survive. So, for those tests we will again try to increase the length by another 1n operation, another read or write operation, and accordingly again we do the simulation till we are satisfied to the extent that 100% fault coverage has been reached, or we have come to the situation where the test length was mentioned and we have done up to that much. Okay. So, then whichever sequence, a number of sequences have been generated. So, whichever sequence give me the best coverage, so we will accept that one.